All right, perfect. Thank you very much for having me. So I'm going to talk about sustainable development and energy efficiency in deep learning, a topic that I've spent quite some years working on. So first, a little bit of an introduction about myself. So I'm a computer scientist and AI researcher at TU Dortmund University. Last year, I finished my PhD on sustainable and trustworthy machine learning and AI. I did both like classic machine learning, but also recently dipped into generative AI, language models, and all that, and also trying to connect this to a bigger frame, not only on the very technical side. I know this reading group is sort of on like technical aspects of deep learning. I'm sort of on a bit higher level in most parts of my research, but I think the value is in connecting that to the deep down essentials. I'm always interested in interdisciplinary projects and transfer, and that's how I got into this reading group as well, because I had nice chats with people about things that we can do. And also on the side note, I'm heading the Young AI Leaders in Dortmund, which is an initiative by AI for Good by the United Nations. So I want to start with a bit of an open question, and maybe you don't have to answer it now. But one thing that grinded my gears when I started my PhD is what are the goals of our research? I mean, of course, starting a PhD, the biggest goal is to get papers accepted and then to write your dissertation and finish your PhD, right? But I also feel that when you talk with people in academia, a lot of people also know that there are bigger goals in life than just our own personal career. And maybe some just do their PhD to earn a lot of money in deep learning, right? But I think there's a lot of people that believe in some sort of goodwill, that have some sort of goodwill, believe in some sort of bigger impact of their work for our world. And a really nice framework that captures this are the Sustainable Development Goals by the United Nations. And sustainable development, of course, this is a much bigger topic. Like we see things like no poverty, gender equality, like these are so big topics, climate action, life on land. How can we connect our research to these topics? And this is basically what I'm interested in. So I will cover four different chapters basically in this talk. I will talk a little bit about the fundamentals of AI and sustainability, and then there's three specific research directions that I went into and explored, and I'm still exploring actually, which is quantifying energy efficiency, then how we can perform benchmarking and meta learning in the goal of sustainability, and reporting and labeling, which is on the sort of interdisciplinary level. Right. So let's talk about AI and sustainability. So I hope that most of you read this paper by Amy van Weinsberger that in the context of sustainability, AI has a twofold role. So on the one hand, we can use it for sustainability. We can use it for driving positive change in our world. As I said, there are sustainable development goals that we can tackle. There's specific projects and initiatives that really focus on specific goals and drive that. I worked with a pump manufacturer from Dortmund. They are doing water technologies. This is clearly linked to the Sustainable Development Goal 6 here. And they are really interested in sustainability as well. They actually place sustainability at the very heart of their whole business strategy. And so it's really interesting how we can use AI in this usage. And another project that we tackled recently is using AI for visualizing political election programs. I'm not going to talk about this here in depth, but this is also something where we did a big interdisciplinary study on. This is currently under review. So this is maybe also an example where we can use AI for sustainability. But on the other hand, we have to also talk about the sustainability of AI itself, because AI, as you all know, has several negative impacts on our society, economy, and environment. So there are these big safety reports. There's people messing with global elections with the help of AI, using it for propaganda and everything, which is sort of the opposite part to what we tried with the Dortmund election AI project. Then there's, of course, the AI Act that sort of tries to regulate AI in a way and to diminish and possibly avoid negative impacts. We have this issue of black box models that are not really transparent and hard to really understand what's going on inside the model. And then we also have this bigger is better paradigm that we observed, especially since deep learning came around. So all these aspects, how can we balance using AI for sustainable and at the same time investigate the sustainability of AI in itself? So one of the things that I asked myself at the beginning of my PhD is what are the causes for the bigger is better paradigm? As I said, model sizes have been blowing up, data set sizes have been blowing up, but somehow we are not really transparent about this big, big like growth in compute. Um, so why is this happening? I found a really nice paper from 2022 that provides some of the answers, I think. In this paper, they analyzed 100 top cited publications from prime AI and machine learning venues. And what they found is that a lot of authors that publish in these venues do not really justify or connect their work to societal needs. There's very few discussions of negative potential, and the justification of why this paper should be accepted is usually based on predictive performance alone. And we also see a big centralization of power here, with the most cited papers usually also being coming from big tech in AI. Um, so these questionable values, I think, also induce this bigger is better paradigm that we see at the moment. So for my PhD, I try to understand how we can advance sustainability. And I think one important thing that we have to do there is that we really acknowledge the multidimensionality and the trade-offs of model performance, which isn't easy to do, but is important to do. There's a lot of different research fields in AI that sort of focus on responsibility, resource awareness, trustworthiness, accountability, reliability. And to me, this is all connected to this framework of sustainability, where we try to balance the needs of the environment, of the society, and the economy. Um, and one specific thing that I think that is interesting is that we can basically connect the classic machine learning focus, where we want to maximize predictive quality, with the efficient ML focus of maximizing resource efficiency. And if we do both things at the same time, or focus on one of them, I think this is really something where we achieve sustainable development, and we can basically advance the Pareto front of this trade-off. And this, of course, is only connecting quality with resources, but you could also put in here fairness, for example, as another dimension that we want to optimize along. At the Lamar Institute, there's two research areas that we in particular focus on, which is trustworthiness and resource awareness, among many other things. So I highlighted them here. And I think you all, in whatever way you frame your research, can connect this to the idea and framework of sustainability. Right. So this is sort of the background on AI sustainability. Now let's turn to the first very specific thing: is how can we quantify energy efficiency in deep learning and in AI and machine learning in general? So we all know how to quantify and optimize the quality of our models, right? We know what a loss function is, we know what an accuracy is, error rates are, whatever you name it. But the question is, how can we really assess environmental impacts? And that's unfortunately not really easy to do. There's some proxies that we can look at. So here for example, I've measured the energy draw here on the x-axis, and I have compared it to the floating point operations and the running time per batch. And you see that there's some correlation there, but you also see that the correlation is not 100%. There's some deviation between these two axes. And we also see that the performance is actually subject to the hardware environment that we use. So on different hardware environments, these numbers can be different. So correlation is good. So we can definitely look at the model size and the running time as a proxy, but we also have to make and be transparent about the possible overheads and estimation errors that we have there. So one thing that I did last year, which is right now just published as a preprint, maybe some of you have heard of Code Carbon. It's a really nice library that has been developed for 5 years now, I think, roundabout, that allows you to track your energy consumption during executing machine learning code. It's really nice. Just pip install Code Carbon, start tracker, stop tracker. You get a report back of energy demand, and they also calculate carbon emissions based on that. So it's really handy for just combining it with your code on running AI and machine learning. But the question is, what Code Carbon does under the hood is it uses NVIDIA SMI, it uses the running average power limit tool by Intel. So it tries to track the main processor resource consumption. But this is something that is not capturing the whole system, right? When you work on a local machine, you might miss out on overhead factors. And especially when you use data and like cloud compute and everything, so like data centers and cloud compute, then the estimation error might be even bigger. So one thing that I did last year is I basically compared the software internal profiling with Code Carbon, which I here call dynamic estimation, because it's dynamically using these tools to measure the current power draw, is comparing that with an external measurement with an energy meter that I tracked with a camera here. So in the first step, this was really like classic OCR. I was really just interested to see what I can vibe code with this using an analog energy meter and a webcam to track this. But we're currently building on top of that. But what we see here is that when we perform a static or dynamic estimation, we have a big offset from the actual ground truth energy consumption. So I profiled a bunch of vision and language models with different sizes. And you see on the left-hand side at 0, you see the ground truth energy consumption. And in relative numbers, you see that Code Carbon underestimates the energy consumption by 20 to 40% roundabout. And you see that the static estimation, which is basically assuming that your processor consumes a static power draw of, say, 160 watt or whatever you configure it to, is overestimating the energy consumption for small models and underestimating it for big models. And this is super interesting, and of course something that we can scale up. These curves basically these scattered traces will look very, very different when we use different hardware, when we use different models, when we use different applications. And I also digged a bit deeper here and, for example, found that Code Carbon is much worse in assessing the CPU energy estimation than when actually using the GPU. And things like the batch size and the temperature of your language models further impact the energy estimation error and the energy estimation itself, of course. So at the Lamar Institute, one thing that we try to focus on recently is, in order to be resource aware and trustworthy, is really allow our researchers to use and understand this energy versus quality performance of our methods. And for that, we introduced the Lamar Energy Tracker, and it basically is a wrapper around Code Carbon mostly. So it's just very easy to use Energy Tracker, pip install it. You can just start and stop it and get a report back. We are currently also extending this to our whole compute cluster, such that every job that is submitted to the cluster is actually also profiled for resource consumption. And basically, whenever people start a job on the compute cluster, they get a mail back saying, using Code Carbon, whatever, the energy consumption of running all experiments on this hardware is estimated to some kilowatt hours. This corresponds to estimated carbon emissions. And this way, people that are not really interested in understanding this like energy estimation problem can use our tool to really make their research more resource aware and sustainable. And what we recently added just a couple of weeks ago is the ground truth tracking that I talked about. And now it's actually extended to smart sockets. So now we don't use a classic like analog energy meter and a webcam, but we use smart sockets, and we use a small Raspberry Pi to act as a server and basically call these smart sockets and ask for the current power draw. And so the next step that we currently set up is connecting a bunch of different hardware devices, running a standardized test bed of machine learning and AI experiments, and measuring the ground truth energy estimation and comparing it with a static and dynamic estimation. So this energy tracker tool that we built is out on GitHub, so you can just check it out, include it for your own research if you're interested. And I think it would be really, really awesome to see more machine learning papers being published that have a statement on energy consumption in them. Right. So next topic, benchmarking and performance trade-offs. So what is clear is that the performance of deep learning methods and machine learning methods in general actually varies vastly across different data sets and execution environments. So one very recent example that I brought is in time series classification. The preprint was actually just published last week. That's the work with Jeff and Angus from Monash University. So I visited them last year and also did my master's thesis with them back then, 7 years ago. And what we investigated is using different state-of-the-art time series classifiers and investing their energy draw in comparison to their balance accuracy on a bunch of different data sets. And that's why we get covariance matrices here, basically. So each model is sort of, it's scattering around values, right? So for example, on the left-hand side, we see that the pruned version of quant is really, really good, has very high accuracy and also very good energy draw. So here, this is relative numbers, so higher numbers always mean improvement. For example, a multi-layer perceptron is much better in resource consumption in general, but it has a lower accuracy. But the interesting thing is when we switch from the CPU to a GPU, this whole distribution of model performance changes completely. So now on the right-hand side, we actually see that the pruned version of Hydra, not the pruned version of Quant, becomes much more resource efficient. And we also see that models like ConfTran, which are like really like transformer models for time series classification, suddenly perform much more efficient which is sort of to be expected when switching from a CPU to GPU, right? Because GPU acceleration just helps these methods a lot. But it's something that people rarely discuss in their papers. Usually, when you read machine learning and deep learning papers, they make claims. And of course, theoretic claims is a whole nother topic, but this is about empirical results, right? And empirical results that are only basically evaluated on a single hardware device, I think is not really expressive of state-of-the-art performance, right? It could be very different. And what you could basically do is sell your method, sell it in a paper by just finding the right architecture for your method such that it beats other methods. Something that I think where we have to really improve our benchmarking skills. Another thing that we did with this paper, as I said, preprint is out now, is we introduced pruning concepts for Hydra and Quant. These are really interesting models because they basically use deep learning features. In the case of Hydra, deep learning features. In the case of Quant, it's actually classic interval features. And then use a very simple linear model, basically, or random forest, like classic machine learning models, to perform the classification of the features. And it's just as good in terms of predictive quality as most deep learning approaches, like pure deep learning approaches, but it's much more resource efficient. And with pruning, we can actually improve the energy estimation. So we see statistical significance in terms of energy draw on the right-hand side. And we see that the balance accuracy is not dropping statistically significant. And we also see this in the two plots here. So the energy draw just decreases the higher we put the pruning rate, but the quality stays pretty much good until we reach like 80% pruning, which is pretty impressive, I think, because we can reduce the model size by 80% and barely lose any quality. Right. So another thing that I did, this is just a short outlook. When we perform a big benchmarking experiment and test like dozens of models on hundreds of data sets, we can actually turn to a different question, which goes into meta learning and model selection, where we want to select appropriate model to train on custom data and hardware based on some suggestion, some meta learning suggestion. So for that, I built AutoXPCR and also assembled another data set, which we called MetaCure, so meta features and meta information for quality and resource awareness. And this also ties to AutoML, of course. So in AutoML, you have a new data set and you want to find the best model without any hyperparameter tuning. So you want to have an automated system that does exactly this for you. Also connecting to neural architecture search and many other different topics. And I spin this into a little bit of a different direction. I basically asked, here are my 20 preset candidates to train on this data. What would be the best model choice to train on this data? And basically, the meta learners here make an educated guess of which model to train. And they do that based on an objective provided by the user. So for example, you could have an objective, just get the lowest error or get the highest accuracy. But you could also input an objective that balances running time, for example, or energy consumption with quality. And that way, the different meta learners in the system can estimate the different properties, and then we combine that into a model recommendation. So in the results, we also found that when you train a bunch of different machine learning algorithms, these are not deep learning algorithms, just standard algorithms, across 200 data sets, tabular data sets in this case, on the left-hand side, you see that the distribution of best model is actually impacted not only by the objective, so whether you want to search the most accurate, the most energy efficient, or the best balanced model, but it's also impacted by the hardware at hand. Just marginally, but still impacted. And our meta learning approach, the blue bars here, is actually able to sort of follow this distribution and really basically adapt to the user needs and user configuration. All right. I think I'm a bit short on time already, so I think I won't explain the other plots, but of course the papers are published, so feel free to read into them if this is interesting to you.
You do have quite some time still, so don't.
Yeah, I just want to have enough time for the discussion as well. There's another topic coming, but I can still shortly. I will just shortly explain the two other plots. So on the right hand side, top level plots. You see that the energy draw is basically going. It's growing on the right-hand side with the amount of models that you test, right? So in this case, we had 11 models in total to test. And when you test all 11 models, then you get 100% of the energy draw. So it's basically an exhaustive search of the model pool. But we see on the left-hand side, by just using the first or the second top two, top three models, that we can already reach 80% of the best actual achievable quality. And so this is another motivation which says we shouldn't just redundantly search model search spaces and train all candidates and just discard all of them except the best one. But we should actually come up with solutions that are a bit more adaptive and that really take into account the features of like the meta features of our data set. And of course, AutoML also tries to be efficient in searching the search space. But what a lot of people in machine learning do is just spend a month testing all different variants, doing like a grid search or something. And then at some point they find the best model, and that's what they report in the paper, and all the overhead efforts are just wasted. And I think this is why model selection and meta learning is so interesting. And at the bottom hand, we see another like side benefit of using such a compositional meta learning approach, where we learn different meta learners for different performance aspects. Because it actually gives us some explanations as well on why we should select a specific model on a specific data set. Because basically you get explanations for the different performance aspects, and then you can trace that back to the meta features of your data. Okay, so that's it for benchmarking and meta learning. Another thing that I want to talk about, and this is a little bit work in progress, but maybe it's still interesting. And if you want to collab on that, then please feel free to reach out. I think what we really need to do as well is look into a more like meta level of benchmarking. So not meta learning, but why and how do we as machine learners perform benchmarks? There's over 20,000 peer-reviewed papers that somehow mention benchmarking in their abstract. But I'm really interested in to what extent they actually acknowledge sustainability. My guess is that a lot of benchmarks are not at all interested in resource efficiency and only interested in predictive quality. And this is something that we want to investigate in our study. So the first question is, what properties and trade-offs are actually encoded in AI benchmarking? This is a bit similar to the paper that I discussed early on. It's like the values in machine learning. I think it would be interesting to understand what values we have when we perform benchmarks. So we performed a systematic literature review to collect all these papers, and we hand-coded 50 of them, the top 50 cited papers, in terms of properties and trade-offs. And now we want to use LLMs to characterize the whole bunch of 20,000 papers, because this is not something that we can do manually, of course. And we can validate with this with our manual annotations, and then we can maybe derive a taxonomy of how we as a community perform benchmarking, and also interpret that with regard to sustainability dimensions. And in the next step, it would be really interesting to see when we use a benchmark that is only interested in predictive quality. So we look at a leaderboard on Hugging Face and see, oh, okay, here's 200 models, and this is their performance, right? Performance in terms of quality. Maybe we can repeat the same benchmark and assess the energy consumption at the same time, and then really investigate the quality resource trade-offs and see how this impacts the state-of-the-art comparison. I already showed you this picture of time series classification, where we see that when we use different hardware and also take into account more than quality alone, the comparison or the ranking of models changes dramatically. And I think it would be interesting to sort of post hoc add that to benchmarks that are already existing. So we want to first identify reproducible benchmarks. Of course, they need to be reproducible if we want to repeat them. And then we want to implement a test suite to repeat these experiments. But at the same time, we measure the energy demand, possibly even across different hardware setups. And then we can use my STRAP framework, which I'll introduce in a bit, to assess property correlations and explore how resource demand impacts the model ranking and scoring. Right. I can give you some first results. As I said, 48 papers have been coded already. And we see that most of them do not offer any resource information. Oh, no, actually, most of them offer medium resource information. Medium resource information here means that they at least report on running time, which is sort of a proxy, as we learned earlier. But high detailed resource information is really just very scarce, and most of them are medium, and a significant part are also no resource information at all. And we see the same with hardware information. So a lot of the benchmarks that we investigated here, or a lot of the papers that we investigated here that in some way mentioned benchmarking, do not offer any information on hardware. And as I said, this is something that I, now looking back on my research experience, I would call that unsustainable in itself. Yeah, there's also very, very few papers that have assessed reliability and privacy, and also fairness and accountability. and human oversight is totally absent, and explainability is frequently mentioned but never benchmarked, possibly because explainability is just very hard to get ground truth information on. So it's not really a nice thing to benchmark, but you can always say, oh, look, we added an explainability mechanism here. You can investigate your model, basically debug it in a way. But if anybody of you knows explainability benchmarks, then please send them over so we can have a look at them as well. Right. So this sort of closes my second topic that I wanted to talk about. Now I can turn to the third topic, and this leaves the actual realm of training models, and it's more about reporting on models. So even if we as machine learners and model developers acknowledge sustainability, we are living in an age where we have to also facilitate sustainable use of these models, right? We have seen that, especially now since the rise of foundation models and language models, like large language models, we've seen that AI is more and more used as a service. And this means that people use the model that are actually not an expert in AI or machine learning at all. You would have the same situation as somebody who just wants to use some technical device, some software, and he can't even read the AGBs because it's too complex. So these people, they need really, really comprehensible information on how and why they should use this model, and also how to not use the model. And because of that, I came up with this idea of rethinking how we as a machine learning community report on the things that we work on. So this characterization here, the first step in my STRAP framework, really starts on the left-hand side with really understanding and characterizing what is the machine learning model that we work on, what is the execution environment that we use it in, so software and hardware, and what is the data set that we use it on. And when we do that, then we derive a bunch of properties that we can collect in an evaluation database. And such an evaluation database, for example, could be used for meta learning, but it can also be just used as a repository, basically, for informing people. It's basically what OpenML attempted to do. It's the same as Papers with Code, who published like leaderboards on this is the different models, these are the connected papers, and this is how they perform. But this is not enough. Collecting this is good, but we also need to think about how we can make this more accessible to people that are not experts in the field, that might not have done a PhD in computer science or data science, and that are just on a more high level. And for these users, I think they have different objectives and they need personalized reports. And in order to inform them, we have to come up with a methodology that allows us to produce personalized reports. And for that, I introduced 4 specific steps. In itself, they are not very complex, but it's important that they are formalized. So we perform index scaling as a way to abstract and to unify different evaluation dimensions. So for example, it's really tricky to compare running time with accuracy because it's just 2 different units. It's even more tricky when we assess the performance on different hardware environments, because maybe the running time improves a lot because we switched from a CPU to a GPU, but maybe this also leads to higher energy demand, right? Because the GPU consumes more energy. So index scaling basically allows us to put any sort of measurement on a relative scale and this way unify it. Then we use compound scoring, which basically means that we project or that we aggregate the different index scaled values onto a compound scale. Compound score, which is based on the objective, which is basically a weighted sum of the different performance metrics. And then we can use rating to color encode this. And then we can also use this to analyze correlations. And I not only conceptualized this, but I also implemented it into a software framework, which is publicly available. And here you see this nice Pareto front that I mentioned earlier, where we have energy draw versus top 1 accuracy and image classification. And you really see that there's not a best model. It really depends on if you're interested in the most energy saving model, which would lead you to MobileNet and QuickNet and all these other sort of like very, very optimized models for inference and low energy demand. But if we want to look at the best quality, then we're up there with Inception ResNet and also the biggest efficient net variance. And this Pareto front is something that users will not be able to understand if you're not having a way to unify the different metrics. Now, you could do the same plot with different hardware environments. I actually did this as well in my in the paper. And on the right-hand side, you see a correlation plot, which is also interesting because it reveals what we as machine learners know. So, for example, there's very high correlation for the accuracy one and also top one accuracy and top five accuracy. We have very, very high correlation there. We also have very high correlation of running time during inference and energy demand during inference. And we have anti-correlation between the running time and energy during inference with the quality of the model, the top one and top five accuracies. But these trade-offs are what really allows people to use AI and machine learning models in a sustainable way. So I think this is something that is super interesting. Oh, Bernard has to leave early. No worries. Thank you for tuning in. um, yeah, so this correlation basically allows us to disclose the trade-offs of our machine learning experiments in a more transparent way, right? Um, and this framework is super generalized, so you can basically upload any sort of evaluation database where you measured performance of different models on different data sets, and it produces these plots for you, and you can just show it to people. And it actually also produces the small energy label here, which I'm turning to now. So um, I think that we have to come up with a bigger communication format that allows us to represent model properties and also suitability for a user in a very, very easy to understand way because nobody has time or will to read through all the papers on image classification. What you really want to have is something like a situation when you go into a store and you're interested in buying a dishwasher and you don't have to be an expert in engineering. You don't even have to know what a dishwasher actually does. You just go in there, say, I have 500 euros. I want to have the most efficient model. And you just buy the one based on your energy label. And this is something that we could establish for AI and machine learning models. Of course, the analogy is a bit tricky because nobody goes into a store and buys an image classifier. But it's something that we can use in domain-specific applications. And that way we can, for example, connect the system developers and the model developers with the sort of steering board level that make high-level decisions on what to actually use in their product, right? So we started with this in 2022 together with Katharina Morik, who had the original idea. And then I sort of used this and transformed it into the energy idea. So in the beginning, it was a general like care label of AI models. And then I adapted this and moved it towards the energy label perspective. And then most recently, we went back and turned this into more general AI labels. And of course, there's some other approaches as well. So, for example, there's been this idea of consumer labels by Seifert et al. In 2019. There's also the question of whether we can assign trust seals to AI models similar to trust seals in e-commerce. So there was some psychological studies on this idea. Then Duran et al. In 2024 basically had a similar idea as we did and then cited our paper and proposed their Gaisan label. And then also last year, Hugging Face, under the lead of Sasha Lucioni as climate lead, proposed their energy score initiative, which is basically also an energy label, just without the performance quality. This is all, the quality of the model. This is all only about energy consumption of the model. So of course, looking at all these different systems, the question is, who needs labels and how can we best represent the information? And this is something where we started off as computer scientists always do, just do things, build a prototype, see if it works. And last year we tried to follow up on this question and actually ground this in a more like interdisciplinary and social study way. So we did a big analysis. We interviewed practitioners, people that are not only active in academia, but actually people that use machine learning and AI in their daily work, and wanted to understand the potential and the limitations of AI labeling in their work. So you see a lot of different people that we interviewed here, mostly male, from different backgrounds. So some of them are just calling themselves like users of AI. Some are engineers that actually build models, and we also had some experts that sometimes even finished a PhD and were really up to the like state of the art and understood all the papers. And we asked them, what are your problems with AI? How do you use AI? What are your requirements on AI? And also, how do you consume information? How do you stay up to date? How do you learn about new models? And basically, We performed a big interdisciplinary coding of this. So what you do with this is you first have the interviews, then you transcribe them, and then you go through all the transcripts and you code every statement that sounds interesting to you and assign it some sort of category in a way. So you see that on the right-hand side, in total, we assigned over 1,000 codes to these interviews. And so it's a qualitative study, right? Not quantitative. But we basically spent a whole paper analyzing these different statements and bringing it all together. And it's a bit summarized here. So there's 4 different research questions that we tackled. Who and why needs labels? So who needs labels and why do we need labels? How do we best label models? What are the competitors? So not competitors in terms of labeling, but how are the workflows, how people acquire their knowledge. And for example, blogs you see were mentioned frequently. And also we asked them about trustworthiness, because trustworthiness is just such a big problem with AI and machine learning. It's basically lowering the acceptance of innovation. So we asked them, could such a label maybe act as a lever for pushing and promoting trust in an AI model? And this was really interesting because there was so many different opinions on this. So some people, for example, said that a label is only trustworthy when the authority behind it is trustworthy, and that makes perfect sense. But when we asked them what is a trustworthy authority for handing out such labels, people were very divided. Some said, well, it has to be a university. Some said, I want to see big tech. But then also people said, well, big tech will oversell their own models. So maybe it's actually not a trustworthy authority for handing out labels. Some said that they actually trust different countries more than others. So it's really a big discussion and something where we found that labeling alone can really solve the issue. So as takeaways, I tried to nail it down. As I said, this is qualitative research, so it's a bit difficult maybe or different from your usual takeaway slides. We are not talking about accuracy percent and everything else here. But what we found is that labels must really strike a balance between providing an overview that is both accessible and meaningful, but at the same time not sacrificing important detail, right? This makes perfect sense. And for AI, it's much harder than for energy labels in like electronic devices, because there's only one metric that you have to report on. And in AI, it's just so different on what you use the model for. You have different metrics, and breaking this down into comprehensible information is just tricky to do, and basically the biggest problem that you have to tackle when you want to establish such a label. Then labels do more than simply present information. They actively shape the decision-making process by highlighting the factors deemed most important. This is something that is super interesting because when we started off the survey, or not the survey, the interviews, we asked them about their requirements on AI, and basically nearly everyone said it's all about quality. It just has to work. It just have to work, and I need to understand that it works well, and I wanna make sure that it's not answering stupid questions wrongly and stuff like that. And nobody was fussed about environmental impacts or energy. Nobody named that. After we showed them our labels, where every label highlights energy consumption, besides quality of the model, many people voiced, well, actually thinking of it, I'm working in a very sustainable company. We call ourselves a green tech company. And actually, energy efficiency is really a big issue in machine learning and AI, and something that we have to think about more often and that we have to address. So by presenting people labels, we nudge them towards sustainable decision making, which is a really, really like potential, big potential and a benefit of such a communication format, and something where I also feel that big tech is sort of, they know that in terms of energy consumption and environmental impacts, they are not really doing well. And so I think their transparency on that end is sort of purpose. Another thing that we found is that labels need to be seen as part of a larger trust building process. So it involves transparency and verifiability and user experience, but it's not a guarantee for trustworthiness, right? This is basically connecting back to this research question 4 that I mentioned. And also labels must allow for customization, ensuring that different audiences can extract the information they need. So in the study, we presented them with labels for image classification. And a lot of people said that this doesn't really apply to their work with AI. They are not really interested in a top 1 accuracy. A lot of them, of course, worked with large language models, and there you have different quality metrics. But even the quality metrics, for example, performance on the MMLU benchmark or something, might not be representative of what they actually do within a large language model in their daily work. They might not even call it a large language model because it's just an API, basically. Maybe not an API, maybe it's just a web page in the chat like ChatGPT. And so understanding quality of this model is just much harder for them. So what we basically concluded in this study is that this idea of a general AI label is just not feasible. What we instead should do is when we have a application context and a use case scenario, then we really have to build a very, very specialized model for this use case and evaluate it with the domain experts at hand to really understand what are their requirements and link that or sort of calibrate it towards the performance of our system and the model that we develop. And this is something that in psychology is called trust calibration. So we just don't want to make people over trust AI or under trust AI, but we want to make sure that the model is actually behaving as they expect it to do. And this is something that we really need to think about how we can do this. So this is sort of concluding my talk now. I know it's a lot of different things, maybe not a classic reading group presentation because I didn't present a single paper, but of course all the papers that I discussed are out there, and I tried to give a bit of an overview for the things that I'm doing. If any of this was interesting to you, then please feel free to get in touch, and also I might send the papers into the chat if you're interested. Otherwise, add me on LinkedIn, and thank you all for tuning in. If you saw this talk afterwards on YouTube, because it's going to be uploaded, and thank you for everyone attending in person here. Yeah, happy to give this talk, and thanks for the invite again.